Hello. So, yeah. So, I am going to talk about not so fast transients with UGMRT. And so this work is done by various people and it is in a not in that much matured state. But some part of it you have already, so if I cover the first transients with GMRT, this first radio burst part we have heard a lot during this conference. And so one part of that is the follow-up of repeating FRBs, and other part is discovering the new FRBs. Other than that, mostly in this talk, I will be talking about the follow-up of study of rotating radio transients, which also can be classified as follow-up of known rotating radio transients and discovery of the new ones. Other than that, there is of course strong pulses from pulsar, which could also be thought of as a progenitor of the first radio burst, and the connection between all these things we have already known about. So these are the faces you all know who are present in the conference and are giving their talks. They have done a lot of work on follow-up of repeating FRBs with UGMRT. So I'm not going to detail of that. But now coming back to discovery of new FRBs with GMRT. So we are conducting the GMRT High Resolution Southern Sky Survey. With that, we have covered this part of the sky, southern sky, with a reasonably high sensitivity. And we have discovered quite a few pulsars, but we have not detected any first radio burst over here. There are some candidates, but so where we saw band limited structures, but manual investigation on those are required. So as of now, there are no FRBs discovered in this survey or with GMRT, I would say. Now I'm coming to what are the rotating radio transients or RRATs. So these are these kind of sources. So from pulsars, we see extremely regular pulses at their spin period. If the pulsar is something called nulling pulsar, then you will see some pulses in here are missed. There are something known as extremely nulling pulsar, where you will see the fraction of nulling is much more. Then there are these RRATs where you sporadically detect these pulses. So, and these RRATs are like very difficult to time because of this sporadic nature. And you will see that in literature, as of now, around 125 RRATs are known, out of which only 30% are known to be timed, and very less of them have long-term timing solution. Okay, so so since we don't have long-term timing solution for most of these, we don't know if they have glitched, if the timing solution that was described in the discovery paper is still holding or not. Okay, so now as Yogesh also had shown in the plot, he had the pulsars and RRATs are unlikely to be the counterpart of FRBs because of their energetics and also the magnetic field. But we can, in this talk, I will try to see the similarities that in the properties of these rotating radio transients and RRATs that we have. So with UGMRT, we have followed 3 well-timed rotating radio transients with simultaneously band 3, which is 300 to 500 megahertz, and band 4, which is 550 to 750 megahertz. And in this table, for one of the RRAT, I have listed the rates at which we detected the pulses in pulses per hour. So where we see that the detection rate is varying a lot, and between 2 frequencies and with one epoch to another epoch, which is kind of similar as is seen for repeating FRBs, that they have certain activity periods and detection rate varies, and again function of frequency. So what we have seen is this temporal changes in detection rate is kind of a similarity between RRATs and FRBs. and this higher detection rate we see in band 4. So that we don't know if that is also the case in FRBs, whether this frequency dependence is that constraint. But for these 3 well-studied RATs, we could see that this band 4, UGMRT band 4, is a space where we see higher detection rate. But I have to also say that this detection rate is also function of telescope sensitivity, which will also be the case for fast radio bursts. So like if you use a telescope like FAST, you will see more number of bursts, but even then it will be dependent on the frequency. So the question is whether we can think of RATs as something like galactic counterpart of repeating FRBs, agreeing on that this energy budget problem, though that this FRBs, if they are like, if they have, if we consider that their distance is like galactic distance, even then we cannot match the energy, the luminosity that we see from FRBs and RATs. So maybe these are, so we don't know, but whether RATs could be the likely counterpart, or maybe there are some more energetic RATs which are yet to be discovered and rare. So, and another thing is repeating FRBs, we don't have, so for RATs in general, these 30% which are timed, we could see the spin periods and the timing model we could get, which is not available for these FRBs, which is a negative point while tallying these 2 sources. But again, 70% of RATs are, we are not able to time them, and also placing these 70% or even this 30% to extragalactic distances, the timing will be even more difficult. Okay, so now coming back to, these are some collection of single pulses that we have detected from this RAT, which is one of the first discovered RAT with the UGMRT. We see different kind of structures in this thing, and some places people may see that the kind of the nature of the emission is kind of similar to what you can see the frequency structure at places are similar to FRBs. So here what I plotted is say this band 3, simultaneous band 3 and band 4 pulses. So this band 3 pulse has the band 4 counterpart is this. So we see that in band 3 generally, I should not say generally, always there is a there is a turnover kind of thing. So at higher part of the band 3, these RATs are not detected, though it is stronger at band 4. So this is indicative of some kind of low frequency turnover for RATs, which is again till now it was not known, mainly because of like not studying with wide frequency wideband telescopes, and also the limitation in number of known RAT, having timing model, etc. So band limited structure is seen for RATs, which is similarity with FRB, and like there can be follow-up studies of RATs and seeing similarity with FRBs and also with the known pulsars. Now I am going to looking at the single pulse spectra, how those compare between RATs, FRBs, and what is known from the literature, in the literature for pulsars. So this is some published data. So Kramer et al. Have studied single pulse spectra for a bunch of normal pulsars, and they have reported the spectral index for single pulse is varying in this range. So though we all know that this like the spectral index, mean spectral index for the average pulses ranges from in this range, though there is some spread between like if depending on which pulsar you are considering, this range may or may not hold. And also, like Rahul have recently published that for a collection of millisecond pulsars, the mean spectral index is varying with time. So temporally, depending on which epoch you are observing, you are seeing different spectral indexes. But the single pulses are known to be varying even more, and Kramer et al. Long back in 2003, they have shown this kind of pattern. So though this is like seen long back, we could not see a lot of literature on this. So on the like variance of the single pulses for the normal pulsars. And also interestingly, for the pulsars that emit giant pulses, there we see the like Crab pulsar, the spectral index range is even more. Single pulse spectral index delta alpha is like the power law index range is around 20 to 25. And also it is, we can see that though there are some part of this thing is spectral index ranges in the negative spectral index, we also have the positive part which is not present over here. Now coming back to again on the IRATs that we were studying, if we plot the distribution, it is more like the giant pulse emitting Crab pulsar, though there are again statistically we are not comparing with many of the giant pulse emitting pulsars for which the data is not available right now. So what we are saying is IRAT single pulses are falling in between the single pulse spectral index range for normal pulsar and the Crab giant pulses. Okay. And the other thing that people generally do while comparing the pulse energetics is they do this flux energy, cumulative flux energy distribution, and it is known that the giant pulse emitting pulsars generally follow the power law trend, whereas the normal pulsars are following the log normal trend, and we found that the IRATs are generally following the log normal trend, though at the high energy tail maybe the power law is better fit. Okay. Now, so I have already told that we have detected some IRAT pulses simultaneously at band 3 and band 4 for 3 of the IRAT. So now if I take one of the IRAT and for one of the epoch to keep the other things comparatively similar. So for one of the epoch, if we stack all the simultaneous band 3 and band 4 single pulses for this IRAT, we clearly see this turnover kind of thing that I was telling, the evidence for that. Okay, so we have here made the stack only using 8 single pulses, but one can again like observe for longer duration and verify this. So there is a turnover kind of thing that is seen. So that lower frequency, we are seeing that this IRAT is showing some kind of turnover. We have fitted. So this is for another IRAT. We see the same thing where we saw after fitting the spectra turnover around 440 megahertz, and for this IRAT again I'm showing the fit where it is again around this value. Though for normal pulsar generally the turnover is seen around 200 megahertz. So for IRATs we see the spectral turnover at relatively higher frequencies around 400 megahertz. So one can check, though in FRBs the band limited signature is much more pronounced, but one can see whether such similarity with this behavior can be found. And I should also give a caution that for the IRAT, where we are seeing there are some simultaneous pulses between band 3 and band 4. For some band 4 pulses, we do not see any band 3 counterpart, which could be due to the turnover happening even at higher frequency than 440 megahertz, so that at band 3, full band 3, which is starting from 300 to 500 megahertz, we are not seeing the pulses. Okay. Now coming, so I have talked about following up of known IRATs. Now I am coming to the discovery of IRATs. So with GHRSS survey, single pulse search pipeline, we have discovered 3 IRATs, and this is the discovery plot of one of the IRAT, though this is a like extremely clean plot. Generally, we have a like this kind of plots where we see discoveries is very much messed up with RFI. And this system is being followed up for timing by Ella from West Virginia. Now, again, the next thing is strong pulses that we can detect from pulsars, whether those can be progenitors for thought of as progenitor for say fast radio burst emission. So regarding that, with GMRT, Saptarshi has worked on this around say 235 giant pulses he has detected from GMRT observation, and he has a poster, so you can, which is displayed here, you can look at it. And also, in addition to this spatial pulsar, there are other pulsars for which Spotlight is continuously taking data, and Ankita today will be talking to us about the strong pulses that she has detected with the Spotlight and how that can probe the possible synergy between neutron stars or pulsars being some kind of connection with the FRBs. So I would now summarize my talk. So I have talked about, so this part is already talked about in this meeting. So I have talked about the rotating radio transients and the possible similarities on the behaviors on, say, temporal detection rate of rotating transients, the similarity in possible spectra and turnover in the spectra, and more comparison of, say, spectra, energy distribution, and more regular observation even of rotating radio transients, and like finding more suitable. So like maybe these 70% of rotating radio transients that are not well timed, maybe one of those are similar, like kind of counterpart of galactic counterpart of FRBs, which can give us some clue on, like, maybe not the full population, maybe some part of it. So yeah, I will leave it you at that, and maybe Ankita can tell us more on the strong pulses. Thank you.
Questions?
So with the RRATs, what I think is that so we have not detected any periodicity in the arrival times of any FRBs, and with RRATs, you'd basically get some period. So how do you think, like whether some FRBs could have periodicities, or
Yeah.
if they can be the progenitors?
Yes, so that's a very good point, that for RRATs in general, the 30% of the RRAT which are well timed, you see periodicity. But what about the rest of the 70%? Out of that, maybe 10% you see sporadic pulses, but like to phase connect that work is not being done. Okay, and yeah, so it is possible that for that rest of the 70% also have defined periodicity, and it is only the matter of more sensitive observations to be put in, regular more sensitive observations to phase connect those. If that is true, then there is like less likely that these like, and also if FRBs do not show any periodicity in future follow-up, then these two populations are not connected. So to know that more, so we need in work in both the places. Yeah, that's it.
Next question.
So, hello. So, at some point, you have said that RRAT has the break frequency is lower than the pulsar. So, why is that?
Yeah. So first of all, this is with limited amount of data. So and only on 2 RRATs. So 2 RRATs which have long-term timing solution, where we could detect multiple bursts in multiple epochs. We have confirmed that for them the turnover frequency, spectral turnover frequency, is around 400 megahertz. For the bursts, here the catch is for the burst which is detected band 3 as well as in band 4. And that selection, those number is very less. So we have to take it with a pinch of salt. But again, this is a fact that we have observed. Now, the reason due to this, to find out the reason due to this, we need to, so generally it is thought that for the normal pulsar, this low frequency turnover is due to free absorption. So one needs to find out, see what are the parameters in those model, and how how we can explain that whether it is varying from RRAT to RRAT. Here, like one needs to do, so this is the result that we are getting.
Yes, sir.
We need to explain it with more data and probably more observations.
Okay, thanks,
Okay,
Vaishali.
thank you.
It's time Vaishali again, and the next speaker is Ankita Ghosh. She's going to talk about giant pulses and their implication in high energy emission and FRB-like activity.
Bhaswati left for the strong single pulses to FRB connection. So in my talk, I'm going to talk about mostly about the bright single pulses from the pulsars and their energy distribution, and if there is any short up connection between the energy distribution of the FRB. So to begin with, as there has been so many talks for past days introducing what FRBs are and all the sciences related to it. So I'll just skip those part and go into what is the most definite part of my work. So to begin with, what is this energy distribution? So by energy distribution, I wanted to mean how often the burst of a specific energy occur within a single source. And for FRBs, we have seen they follow their energy tail follows a power law, which is given by this equation here, and which basically means how quickly the high energy events thins out as we move toward the higher energies. So here, if we get these alpha values to be very smaller than, greater than -1, we say that we are getting a flatter energy tail. That means the burst of those energies are not that rare, they are pretty common. However, if we are getting this alpha value to be even smaller than -2, that means that the bursts are extremely rare. And why is it important? Because this can determine the detection rate of FRBs and also can hint us toward the underlying emission mechanism of the FRBs and their possible progenitors, like people discuss, like Newton star pulsar and the magnetars, LPTs, etc. So this is an example plot that I have taken from Zhang et al. 2022, where they have shown the cumulative energy distribution for the FRBs, and so the upper panel shows the energy distribution with the power law index plotted in the panel B, and the panel C shows the energy distribution of the bursts. So our aim of this work was to analyze this energy distribution of the pulsars and compare their energy tails with the FRBs, and to see whether if there is any connection between the FRBs and the pulsars that we can make. As there has been so many FRBs recently discovered, some of them shows flat energy tails and some of them are showing high steep energy tails. So there has been a recent study also comparing these the energy tail property of the FRB and the pulsar. So one example of these of that is this work where this Zhang et al. 2095 they have shown that the RRATs mostly shows a flat energy tail, which is similar to many of the FRBs. However, there is also FRBs that shows a intermediate energy tail slope that is nearly -1.5, that is FRB 201 to 1102A. So I have taken this plot from Zhang et al., where the first panel here shows the energy tail of the FRB 20201124A, and then this plot shows the energy tail slope of the RRAT, and we can see the power law index alpha is kind of similar, and both shows flat X spectra. So building on this work, we tried to see if this correlation exists for a larger population of pulsars emitting strong pulse, single pulses. So for that, we have selected available bright pulsars from the spotlight data, and these are the list of those pulsars. So this is the observation detail of the sources that I have used in my work, and you can see that most of the pulsars, like out of 6 sources, the 4 sources are observed in the band 4, and one was in the band 3, and another was in the band 5, and the detection significance for the folded profile corresponding to this observing duration for the sources are given here. And so now I'll talk about the analysis process that I have followed. So we got filter bank data from Spotlight as an input. Then we redisperse the filter bank at the DM of the pulsar and search for the single pulses at the pulsar periodicity. Then we compute the signal to noise per pulse, and we clean the RFI of those pulses using PSRchive module PAS. And then finally we kept the candidates that have a signal to noise ratio greater than 7. And then we calculate the off-pulse baseline, which we used to apply radiometer equation to calibrate the single pulse flux density, and thereby getting the pulse width, we calculated the fluence. And then we use these specific isotropic energy equation to get the energy distribution of the pulses, which is ES. And now to compare the energy tail distribution across the sources, we have normalized the energy distribution of the pulses by the highest, by the brightest pulse of that particular source. So then we built a cumulative distribution function where n is the number of bursts above energy E and alpha is the Paolo index of that high energy tail. And then also, if so that we can compare ideally between the different sources that I have started, I also defined a density that is like number of bursts per bin divided by total burst. And then we use simple SciPy curve fit as of now and fitted Paolo to get triple Paolo to get low, mid, and the high energy regimes of those Paolo distribution, energy tail distribution. So after doing all the analysis, this is the final number of single pulses detected for all the sources that I have studied. And this is the average fluence distribution for the pulses that I have studied. So this is the energy tail that we have obtained for our target sources, and here I have to mention this is the low energy regime, which we don't consider for sciences here, and also for this high energy tail, which shows very steep spectra that steep Paolo index, as we can see, but this part of the energy tail, the beams in that part of this part of the energy tail doesn't contain much of the burst. So as of now, I am not considering this part of the Paolo index. So we'll mostly focus on this intermediate part, where for some pulses we have got flattered Paolo index. For some we got quite steeper as expected from CRAP. And these are the energy tail distribution for other sample pulsars. So here's the summary of the slopes that we got for the pulsars that we have studied. And from literature, I have collected the slopes that we see for the FRBs, for the repeater FRBs till now. And if we look very carefully, we see there is kind of a similarity in the Paolo index between the intermediate slope for Paolo index for the intermediate slope of the pulsars and the FRB slopes. And if we look into more carefully, we can see that there are some FRBs within the repeater shows Paolo index which are flatter, but there are FRBs that shows steeper also, and that has quite similarity with the pulsars. So I have categorized which of the pulsars in my sample shows steeper and flatter Paolo index, and correspondingly which FRBs are showing flatter and the steeper slopes. Other than energy tail, we have also tried to compare the spectral index distribution for the FRBs that is available in the literature, and with the single pulses that already Bhaswati mentioned some part of it for the strong pulses of the pulsar. And we can see there's a like wide distribution of the spectral index from -15 to +10, and which kind of follows like normal Gaussian distribution. And if we look at the other like spectral index distribution for the single pulses for crab, if we plot like giant for crab, the giant pulses also shows the similar kind of spectral index. However, for the normal pulsars emitting just single pulses, we see that spread is not that wider; it's quite narrower, -4 to -0.5. And I have done similar, like I've started doing similar analysis for some of my target sources, and we see for crab, we also got similar kind of a spectral index distribution, and for other two pulsars for my sample also shows the similar kind of a spectral index distribution. However, those are not as like wider as the crab. And why I have tried to do like started both spectral index and energy tail. So this is like one of our idea is to model both energy and the spectral index distribution jointly to disentangle the inherent emission mechanism of the FRV from their like propagation effect. To conclude, from our study, we have seen that if the bright pulses from the normal pulsars shows quite similar energy tail slopes with FRB, where we see that within the repeater of the repeater class of the FRBs, some FRBs has a flatter energy tail index, Powell index, and some has steeper. And this we see for pulsars also we see similar kind of distribution. Again, the other studies shows the RRATs also shows that flatter energy distribution resembling some of the FRBs. So all those things together kind of hinting maybe this pulsar or RATs share similar kind of physics in for like emission mechanism with the FRBs, and depending on their environment and other things. And in addition to that, we have seen also that there's a spectral index overlap. Like the behavior of the spectral index is almost similar for the single pulses and the FRBs that has been seen till now. And so it can also show probably their emission region or and the propagation whatever is like those are keeping an imprint on their spectral behavior. And so I'll end with this question. So probably the repeater FRBs also have two subclasses with flatter and steeper energy tails, implying there are like two different or multiple emission routes for them.
Thanks, Ankita. There are questions now? This one?
Thank you very much. Could you say again why you focused more on the intermediate part than the high energy tail? And also, how do you determine where your completeness threshold is? Like to which energies, to low energies are you complete in the energy distribution? Sorry, I'm talking about the energy. Yeah.
So to answer your question, so first, so this is in a very early stage of work, and we don't have enough number of bursts and for the high energy regime. So I don't know how reliable those like this side of the power tail are. There's very even for the FRBs also that I've seen like in many literatures there is no like not sufficient detection of very high energy bursts are available. So people don't consider this part of the bill. So that's why as of now I have like not relying on this part, but we can reconsider it after I add even more pulses from the similar source or like increasing our sample sizes. And for this, like you were asking about these boundaries?
No, about the completeness threshold. So you will only see bursts that are higher than some threshold, right? Otherwise they're too faint for the telescope. And so this will naturally make a shallow shape towards the left. And so the question is, where is this completeness threshold?
For now, I have like taken this intermediate region, like the burst that lies in this region by just minimizing the standard error on their energy distribution. Yeah.
There are not any more questions. Let's thank Ankita. To the discussion session of